Ancient sailors crossed oceans we would still fear to navigate. They found tiny islands in endless blue water and established trade routes across thousands of miles, all without any of the technology we rely on today. This leaves us with a profound historical mystery. What brilliant, forgotten tools did they use to perform these impossible journeys? For every famous compass or astrolabe that survived, dozens of other ingenious devices have vanished from history, lost to time, secrecy, or catastrophe. In this exploration, we are going to uncover 25 of these lost ancient navigation instruments. You will discover the secret methods that guided humanity across the planet, from mental maps of the stars to legendary crystals that could see the sun on a cloudy day. We will see how Viking sunstones might have worked and why Arab sailors guarded a simple wooden board with their lives. By the end, you will see the ancient world not as a primitive place, but as a landscape of sophisticated innovation, where every voyage was a triumph of human ingenuity over a vast and unknown sea. What forgotten piece of ancient wisdom would you want to rediscover? Our first lost instrument was not made of metal or wood, but of memory and sky. The Polynesian star compass is a breathtaking example of how the human mind itself can be the most sophisticated tool for navigation ever devised. Picture the vast Pacific Ocean, an expanse of water so immense it covers nearly a third of our planet. For the ancient Polynesians, this was not a barrier but a highway. They settled islands from Hawaii to New Zealand to Easter Island, crossing thousands of miles of open sea in double-hulled canoes. They did this without maps, without written records, and without any physical compass. Their instrument was a living, mental construct, a celestial map etched into the mind of a master navigator. This star compass was not a single circle, but a complete understanding of the night sky as a moving, directional guide. A navigator would memorize the precise point on the horizon where hundreds of specific stars would rise and set. The sky was divided into houses or directional sectors, like the invisible spokes of a giant wheel centered on the canoe. The rising point of the star Arcturus might define one house, while the setting point of the Southern Cross defined another. Each star was a beacon, and as the Earth turned through the night, new stars would take their place, creating a rotating dome of reference points. The navigator did not just look at one star, they felt the entire dome turning above them, knowing their position by the relationship between these celestial markers and the rhythm of the ocean swell. This knowledge was a sacred treasure passed orally from teacher to student over years of rigorous training. It was a dynamic system, constantly updated by observation, allowing them to correct for seasonal shifts and sail directly to a target island that was far beyond the horizon. The star compass was a perfect fusion of astronomy, intuition, and courage, a lost instrument of the mind that turned the greatest ocean on Earth into a familiar path. Yet for all its brilliance, the Polynesian star compass required a clear night sky. But what happened when the heavens vanished, swallowed by the dense, gray fog of the North Atlantic? Here, another legendary instrument emerges from the mist, one that seems to border on magic. The Viking sunstone, or solarstein, is mentioned in Norse sagas as a mysterious tool that could reveal the sun's location even when it was completely hidden by cloud. For centuries, this was dismissed as pure myth, a fanciful story of enchanted crystals. Modern science, however, suggests the sagas might have been recording a profound technological secret. The leading theory points to a transparent crystal known as Iceland spar, a form of calcite that possesses a unique property called birefringence, or double refraction. When you look through a clear piece of Iceland spar, you see two images of everything behind it. This happens because the crystal splits light waves into two separate beams. Crucially, the sky itself emits polarized light, with its pattern shifting in a predictable circle around the hidden sun. A skilled navigator could hold such a crystal up to the sky and slowly rotate it. When the two faint, overlapping images seen through the stone merged into one single, clear image, the crystal would be aligned with the polarization pattern, pointing directly toward the sun's position. This would work not only through thick overcast, but even during the twilight hours after sunset or before dawn, granting the Vikings a celestial compass when no star or sun was visible to the naked eye. The debate moved from legend to tangible evidence with the discovery of a piece of Iceland spar on a 16th century English shipwreck off the Channel island of Alderney. Found near navigation tools, it stands as the best physical candidate for a real sunstone we have ever uncovered. Imagine the scene, a longship battling the rolling swells under a featureless grey dome. The navigator, unable to see land or sky, pulls a milky crystal from a pouch. He holds it aloft, turning it slowly until the light within it changes, and with calm certainty, he points the way to Greenland. This was not magic, but a masterful application of hidden physics, a lost key to the Vikings' incredible reach across the northern seas. But the Vikings were not the only ones with a secret for measuring the sky. Far to the south, in the warm waters of the Indian Ocean, Arab and Swahili traders mastered a different kind of celestial navigation with a tool of deceptive simplicity. The camel was nothing more than a small rectangular piece of wood about the size of a credit card, with a knotted string passed through its center. Yet in the hands of a skilled navigator, this humble board became a precision instrument for locking onto a single line of latitude. Here is how it worked. A sailor would sail north or south until he reached his desired latitude, the invisible east-west line circling the globe where his destination port lay. To mark this line permanently, he would take his camel and hold the string at a specific knot between his teeth, then extend his arm fully. He would slide the wooden card along the string until its bottom edge lined up perfectly with the horizon, while its top edge touched a specific guide star, most often the North Star Polaris. Once this measurement was set, the knot on the string was tied permanently. From that moment on, no matter where his ship sailed, the navigator could return to that exact latitude simply by holding that same knot in his teeth, extending his arm, and sailing east or west until the star just kissed the top of the board again with the horizon at the bottom. It was a brilliant physical memory, a three-dimensional bookmark in the sky. This made the camel incredibly powerful for Indian Ocean trade, where merchants sailed between known ports all lying on roughly the same latitudes, like from East Africa to India. The navigator did not need to know his exact longitude, a problem that would stump Europe for centuries. He just needed to find his latitude highway and sail straight along it. Because of its devastating simplicity and effectiveness, the knowledge of how to use a camel was a closely guarded trade secret for generations. A master would teach only his most trusted apprentices, ensuring that control over the lucrative spice and silk routes remained in the hands of those who held the knots. It was a secret written not on parchment, but on a piece of string and a scrap of wood, a lost key to the wealth of an ocean. While the camel used a single star as a fixed guide, another civilization sought to build a guide that would never move at all. Far from the open sea, within the courts of ancient China, engineers created one of history's most astonishing mechanical marvels, the south-pointing chariot. This was not a maritime tool, but a land-based navigation instrument of breathtaking complexity. Imagine an ornate wheeled chariot, part of a grand imperial procession. At its center stands a small, detailed figurine, perhaps a celestial official or a mythical creature. Its outstretched arm does not wave or turn with the chariot. No matter how many corners the procession takes, no matter how many winding paths it follows through palace grounds or across battlefields, that figurine's arm remains locked, perpetually pointing toward the south. This was not magic, but a masterpiece of mechanical engineering, a physical compass built centuries before the magnetic needle became common. The secret lay inside the chariot's housing, a system of interlocking gears so advanced it would not be seen again in the West until the differential gear of the modern automobile. As the chariot's wheels turned, they drove this hidden gear train. The genius of the system was its compensation. The gears were designed to account for the difference in rotation between the two wheels when the chariot turned. If the chariot turned right, the left wheel would travel a greater distance, and the gears would automatically adjust, rotating the figurine on its platform to the left by exactly the same amount, keeping its arm pointing in the original southern direction. It was a mechanical brain performing instant calculations to maintain a constant bearing. Historical texts like those from the Han Dynasty scholar Ma Jun describe its invention and reinvention over centuries, often presented as a tribute to the emperor's cosmic authority, a symbol that his reign was in harmony with the heavens. On a practical level, such a device would have been invaluable for organizing large military formations in featureless terrain or maintaining ceremonial direction during long, elaborate processions. The true engineering mystery is not whether it worked, texts are adamant that it did, but how such precise differential mechanics were conceived and crafted with the materials and tools of 2,000 years ago. Each chariot was likely a unique artifact, built by master artisans whose understanding of motion and compensation was lost and rediscovered multiple times. It stands as a monument not to maritime exploration, but to a different kind of human quest, the desire to build a perfect machine that could defy confusion and always know its way. The quest for a perfect mechanical guide finds its most baffling echo in a corroded lump of bronze pulled from a Roman shipwreck. The Antikythera mechanism is often called the world's first analog computer, a stunningly complex clockwork device used to model the cosmos. But beyond tracking Olympic Games or planetary motions, a compelling question remains: could this ancient Greek masterpiece have also been a secret weapon for navigation? Its intricate gears, driven by a hand crank, could predict the positions of the sun and moon, the phases of our satellite, and even coming eclipses with remarkable accuracy. For an ancient captain, this information was not just academic, it was vital for survival. Knowing the precise phase of the moon was essential for predicting tides, which could mean the difference between a safe harbor entry and a shattered hull on hidden rocks. Predicting an eclipse, a terrifying event often seen as a divine omen, could prevent a crew from panicking and abandoning ship, but the mechanism's potential goes even deeper. Some researchers theorize its outputs could have been used in a method called lunar distance, a technique for estimating longitude centuries before it became standard practice. The concept involves measuring the angular distance between the moon and a specific star. Because the moon moves quickly against the starry background, this distance changes predictably with time and, crucially, with your position east or west on the globe. If the Antikythera mechanism could accurately predict the moon's position relative to certain stars for a given date, a navigator could make an observation at sea and compare it to the device's prediction. The difference between what he saw and what the machine forecast could reveal his longitude. While this would require precise observational instruments and mathematical skill the device itself did not provide, the mechanism could have generated the crucial reference tables needed for the calculation. More simply, it could have served as an unerring celestial calendar. Before a long voyage, a captain or a sponsoring merchant might consult the device to learn the best dates for departure based on planetary alignments or moonlit nights, plotting a course using a pre-calculated astronomical schedule. The true extent of its navigational role remains one of history's great puzzles, as ongoing research using advanced three-dimensional scanning continues to reveal new inscriptions and gear functions on its fractured faces. Was it a philosopher's teaching tool, a rich man's planetarium, or the secret brain behind ambitious sea voyages? Perhaps it was all three, a testament to a lost age where understanding the heavens was the ultimate key to mastering the earth. While philosophers built cosmic computers, the foundation of all trade and empire began with a much simpler question: how deep is the water? In the fertile floodplains between the Tigris and Euphrates rivers, the world's first great civilizations rose not on the open sea, but along winding, unpredictable inland waterways. Their most vital navigation instrument was the river plumb, a deceptively simple tool that shaped history. Picture a Sumerian or Babylonian boatman guiding a heavy-laden barge of grain, pottery, or timber. The river before him was a shifting maze, its channels constantly reshaped by seasonal floods that deposited new sandbars and silt in unpredictable places. Striking one of these hidden barriers could mean a broken hull, a sunken cargo, and economic ruin. His solution was a length of rope with a heavy stone or lump of lead tied to its end. Standing at the bow, he would swing this weighted line forward into the murky water, feeling the rope play out through his fingers until the weight thumped softly against the riverbed. By noting marks on the rope, often just knots tied at regular intervals, he could instantly gauge the depth. This real-time data allowed him to choose the deepest channel, navigate treacherous bends, and call out warnings to following vessels. The Mesopotamian river plumb transformed chaotic rivers into predictable commercial highways. It enabled the regular, large-scale transport of goods that fed the cities of Ur and Babylon, carried the laws of Hammurabi, and supported the vast administrative machinery of empires. This humble tool did not point to the stars, it listened to the mud, and in doing so, it made the first controlled, repeatable journeys possible. The principle was so fundamental that it never became obsolete, it simply evolved. Centuries later, Mediterranean and European sailors facing the unknown depths of the ocean adopted the same idea, creating the lead line. Their version was more sophisticated, with the weight often hollowed out and filled with tallow, a sticky animal fat. When the lead hit the seabed, the tallow would pick up a sample of sand, shells, or mud. By bringing this sample up and examining it, a sailor could not only know the depth but also identify his location by matching the seabed composition to notes on his coastal chart. From the silt of the Euphrates to the ooze of the Atlantic, this was the direct lineage, a tool born from river trade that would eventually help map the contours of the entire ocean floor. It reminds us that before humanity could conquer the sea, it first had to learn to listen to the bottom beneath its feet. The river plumb listened to the mud, but Viking navigators faced a horizon with no bottom at all. To conquer the open North Atlantic, they needed tools that could capture the sun itself. Among their most practical devices were two interconnected instruments, the horizon board and the bearing dial, which turned daylight into a reliable compass. The horizon board was likely a simple wooden disc marked around its edge with notches or carvings representing the cardinal directions. At its center, a small vertical pin called a gnomon would cast a shadow. As the sun moved across the sky from sunrise to sunset, the tip of that shadow would trace a curved path across the board. A navigator who knew the date and his approximate latitude could compare that shadow's arc to pre-marked lines on the wood. If the shadow fell to the left of the correct line, it meant he was sailing too far south, if to the right, too far north. This was not just a sundial for telling time, it was a lateral guidance system, a way to check and correct one's east-west course throughout the long, sunlit summer days of the northern seas. It provided a constant, physical reference in a world of shifting waves and endless blue. This principle of using the sun's shadow was refined into a more specialized tool, the bearing dial. Our best evidence for this comes from a single, half-charred fragment of a wooden disc discovered at a Norse farmstead in Greenland. On one side, it bears a series of carefully inscribed lines that radiate from a central hole like the spokes of a broken wheel. Researchers believe this was a portable sun compass. Before a voyage, a navigator would calibrate it for a specific time of year. He would insert a central gnomon and then, at local noon when the sun reached its highest point, rotate the dial so the gnomon's shadow fell along the correct radial line for that date. Once set, the dial would then indicate direction for the rest of that day as long as the sun shone. It was a snapshot of the sun's behavior, captured in wood, allowing a crew to maintain a steady bearing even as cloud banks momentarily obscured their celestial guide. These tools did not work in isolation. They formed a layered navigation suite. On a clear day, the bearing dial or horizon board provided primary guidance. When fog rolled in, the sunstone could locate the hidden sun to reset the instruments. And when all else failed, Viking sailors relied on a profound, accumulated wisdom of the natural world. They watched for specific seabirds, knowing certain species would fly out to sea to fish at dawn and return to land at dusk, revealing the direction to shore over 100 miles away. They learned to read the subtle patterns of ocean swells, feeling how waves refracted around distant islands, creating a telltale interference pattern on the open water that could be sensed by the roll of the ship. The horizon board and bearing dial were the technical heart of this system, physical anchors for a vast, living knowledge that turned the terrifying emptiness of the North Atlantic into a navigable space, paving the way for settlements in Iceland, Greenland, and beyond. The Vikings' mastery of sun and shadow was profound, but it was limited to the daylit half of the world. For cultures navigating under the vast, star-filled skies of the Middle East, the night itself was the primary chart. Among the most sophisticated and elusive of these nocturnal tools was the Persian Khorramabad night traverse table. This was not a simple wooden board or a crystal, but a complex astronomical instrument, likely crafted from brass or engraved on a flat tablet, designed to unlock a ship's position from the silent dance of the stars. Its purpose was to calculate latitude at night by measuring the precise altitude or angular height above the horizon of specific fixed stars. Imagine a Persian navigator on the deck of a dhow in the Persian Gulf. He would use an instrument like an astrolabe or a simple quadrant to measure the angle between a bright star, say Sirius or Vega, and the horizon. He would then consult this traverse table, which contained pre-calculated mathematical data. The table would essentially tell him, if you see this star at this specific angle on this date, then you are at this specific latitude. In theory, it was a stellar GPS receiver carved in metal, a direct translation of the heavens into a map of earthly position. The immense challenge, and the reason such a device borders on legend, was time. To be accurate, the table needed to account not just for the star's position, but for the exact moment of the observation, because the stars wheel across the sky throughout the night. Without an accurate marine chronometer, which the world would lack for another 800 years, knowing that precise moment at sea was nearly impossible. The existence of the Khorramabad table is inferred from advanced medieval Islamic astronomical texts, which describe such calculation methods and reference star tables used by navigators. Persian and Arab astronomers like al-Biruni and al-Sufi produced incredibly precise celestial catalogues and developed complex spherical trigonometry. It is a short, logical step to believe that someone, perhaps in a center of learning like Khorramabad, attempted to condense this formidable knowledge into a physical instrument for mariners. Yet no such device has ever been found in an archaeological context. Was it too valuable, passed down until it wore out? Was its construction so rare that every example was melted down? Or did the fundamental problem of timekeeping mean it remained a brilliant theoretical concept, a navigator's dream etched in scholarly manuscripts but never truly forged in brass? Its ghost lingers in the pages of those old texts, a promise of nocturnal precision that the ancient world could almost but not quite grasp. The ghost of the Persian star table speaks to a world that tried to measure the heavens. But what if the most reliable guide was not above but all around you, in the very motion of the sea? On the island of Crete, long before classical Greece rose, the Minoans built a dazzling maritime empire. Their vibrant frescoes show graceful ships sailing between ports, and their artifacts are found across the Aegean. They ruled the waves for centuries without any surviving evidence of complex navigational tools. Their secret may have been an instrument you could not hold in your hand, but one you learned to feel in your bones. We might call it the Minoan wave reader, a profound, codified understanding of the sea's rhythms. The Aegean is a complex basin dotted with islands, and this geography creates a unique marine signature. Waves and swells do not simply roll in from the open Mediterranean, they bounce, refract, and intertwine. A dominant swell from the northwest, for instance, would hit the western cliffs of an island and scatter, creating a distinctive interference pattern in the water to its leeward side. Another swell from the south might wrap around a different landmass. The Minoans, sailing these same routes for generations, could have learned to read these patterns like a road map. A seasoned captain standing at the helm might feel a particular set of intersecting rhythms through the hull of his ship, a specific dance of peaks and troughs. That feeling alone could tell him he was in the channel between Thera and Crete, or approaching the sheltered bay of Knossos, even if both lands were still below the horizon. This knowledge would have been a living instrument, a sensory database built from 1,000 voyages. It was likely passed down orally from master to apprentice, a sacred lore of the sea. Perhaps it was even recorded in some form on the clay tablets of their palaces, written in the still undeciphered linear script. Those tablets that survived fire and time are almost all inventory lists, but what if others held wave codes or sailing directions? We will never know, because this entire system of knowledge vanished when the Minoan civilization collapsed around 1450 B.C., likely due to a cataclysmic volcanic eruption and subsequent invasion. The intricate wave lore, the mental charts of swell and reflection, died with the last navigators who understood it. Later Greek sailors would use basic wave reading, but the deep, systematic mastery that turned the chaotic sea into a predictable grid of energy, that was a lost instrument. It suggests that the greatest navigation tool of all might not point to the sky, but listen to the silent language of the water itself. The Minoans' mastery of the sea was a living tradition, but for an empire built on law and logistics like Rome, such knowledge had to be written down. Long before the exquisite medieval portolan charts with their precise coastlines and web of room lines, Roman navigators relied on their own sophisticated guides, now lost to time. These were the precursors to the portolans, likely based on documents known as periploi. A periplus was not a map in the modern sense, but a detailed sailing log, a sequential text describing a voyage from port to port. It would list distances between landmarks, describe the nature of the coastline, note the location of safe harbors and freshwater springs, and warn of dangerous shoals or hostile tribes. Imagine a Roman sea captain, his ship laden with grain from Alexandria bound for Ostia. His most precious cargo might be a roll of parchment or vellum, a periplus for the Mediterranean. It would not show the sea as a blank space, but as a linear narrative of practical advice. Sail 100 stadia past the temple on the headland, it might say, until you see a river mouth with red cliffs, there find a safe anchorage on the eastern bank. These logs were the accumulated intelligence of centuries of commerce and naval patrols. Scholars believe that over time, these textual descriptions evolved into drawn illustrations. A scribe might sketch the coastline described in the periplus, adding simple symbols for ports, mountains, and hazards. The most critical innovation would have been the wind rose, a circle marking the directions of the 8 or 12 major winds, which were named and well understood by Roman sailors. This simple diagram would allow a captain to translate the written instructions, sail east with the Eurus wind for a day, into a visual course on the sketch. These combined documents, the text and the sketch, formed a complete nautical guide. Their loss is a historical catastrophe. Made from perishable animal skins, very few could survive the damp conditions of a ship or the ravages of time. We have fragments of periploi texts, but not a single accompanying Roman sea chart has ever been found. This loss leaves a silent gap in the center of the Roman world. We can trace their roads with stone, but their maritime highways, the true veins of their empire that carried the grain to feed Rome and the legions to conquer provinces, are ghost lines on a missing map. The medieval portolan charts that appear centuries later, startlingly accurate and seemingly out of nowhere, may well be the distant descendants of these Roman working documents, copied and refined in secrecy by Mediterranean navigators through the Dark Ages, a fragile thread of practical knowledge that never quite snapped. From the written logs of Rome, we cross an ocean to a civilization that left no written records at all. The Olmec, the mysterious mother culture of ancient Mesoamerica, thrived in the steamy lowlands of what is now Mexico over 3,000 years ago. We know them for their colossal stone heads, 17-ton portraits of rulers with enigmatic expressions, hewn from basalt and moved dozens of miles through swamps and rivers without the wheel or draft animals. If they could orchestrate the movement of these monoliths, what other sophisticated knowledge did they possess for navigating their world? While the Olmec are famed as the originators of the Mesoamerican ball game and a complex calendar, their potential as master navigators is a haunting mystery. Their heartland was a network of rivers and lagoons, with key sites like La Venta and San Lorenzo positioned for waterborne trade. Canoes were their trucks carrying jade, obsidian, cacao, and rubber across a landscape where jungle made overland travel nearly impossible. To coordinate this trade, they would have needed more than just a strong paddle. They needed timing. This is where the idea of an Olmec celestial almanac emerges. The Olmec calendar system, a precursor to the famous Maya-long count, was deeply tied to astronomy. They meticulously tracked the cycles of Venus, the brilliant morning and evening star, which held immense religious and practical significance. The appearance of Venus in the dawn sky marked specific periods in their ritual calendar, but it could also have served as a celestial clock for commerce. Imagine an Olmec trader preparing a shipment of polished jade celts from the highlands to the coast. Consulting a learned calendar keeper, he might be told the optimal date to depart, when Venus would rise in a specific constellation, signaling the start of the dry season when river levels were predictable or when celestial alignments promised safe passage. This almanac would not have been a book as we know it, but perhaps a series of carved jade plaques or painted codes on now vanished wooden tablets that correlated the 584-day cycle of Venus with seasonal weather patterns and sacred geography. The knowledge of how to read these cycles for practical travel would have been a form of power held by a priestly elite. It transforms their colossal heads from mere monuments into evidence of a logistical genius. Moving a single head required knowing the wet and dry seasons intimately, understanding which river routes were navigable with such a load, and coordinating hundreds of laborers. This was not brute force, it was applied celestial and environmental engineering. When Olmec society declined around 400 BC, their major centers were ritually defaced and abandoned. The deep jungle reclaimed their plazas, and the specific, practical knowledge encoded in their celestial almanacs, the very schedules that may have guided their trade empires and megalithic transport, faded into silence. Their stone heads remain, staring out from the past, guarding the secrets of how they ever arrived at their final destinations. While the Olmec almanacs used Venus to time journeys across rivers, ancient Indian scholars dreamed of a machine that could command the entire cosmos. The Yantra Raja, or King of Instruments, is perhaps the most ambitious and mysterious device in the history of navigation, existing only in tantalizing descriptions within Sanskrit astronomical texts. It was not merely a tool, but a theoretical masterpiece, a comprehensive brass engine designed to model the heavens with such precision it could guide a ship across any ocean. In its grand ambition, it stands as a conceptual cousin to the Antikythera mechanism, but the texts suggest it may have aimed for even greater scope. Where the Greek device tracked cycles and predicted eclipses, the Yantra Raja, as described, was meant to be a dynamic, all-in-one navigational computer. Its intricate gearwork, powered by water or weights, was said to simulate the motions of the sun, moon, and planets against a fixed backdrop of constellations. A captain could, in theory, input the date and consult the machine to see the exact night sky he would encounter on his voyage, learning which stars would be his guides and when they would rise and set. But its proposed functions went far beyond stargazing. The texts claim it could predict the complex ebb and flow of tides, a vital calculation for entering treacherous river mouths or coastal harbors. It could plot a course by calculating the angular relationships between different celestial bodies, essentially performing spherical trigonometry with turning gears. Most astonishingly, some interpretations suggest its design might have even attempted to account for magnetic deviation, the subtle difference between true north and the direction a magnetic compass points, a problem European sailors would not understand for over 1,000 years. This idea hints at a profound, almost prescient grasp of the Earth's invisible forces, yet for all its glorious description, the Yantra Roger remains a ghost. No physical example has ever been found, nor any detailed engineering plans. It lives in the realm of Siddhanta, the classical astronomical treatises, as the ultimate expression of a scientific ideal. Scholars debate fiercely, was it ever actually built? Or was it a brilliant thought experiment, a blueprint for what was possible, created by mathematicians who possessed the knowledge to conceive it, but perhaps not the artisanry to forge its impossibly complex parts? It represents the pinnacle of a lost scientific tradition, where the line between advanced engineering and philosophical speculation blurred. The Yantra Roger challenges our view of history, asking us to consider not just what was made, but what was dreamed. In the silent libraries of ancient India, the idea of a machine that could tame the stars for navigation was born, a king of instruments that may have ruled only in the minds of geniuses. The Yantra Roger was a dream of celestial control, but on the dark decks of Phoenician trading ships, navigation was a matter of gritty, real-time calculation. These legendary merchants of the Mediterranean, who sailed as far as Britain for tin and possibly around Africa, left almost no written records of their methods. Their tools, crafted from wood and rope, have long since dissolved in the sea. Yet to maintain their mercantile empire, they must have possessed a reliable way to measure the most critical variable during a night passage, time itself. For dead reckoning, the practice of estimating one's position based on speed, direction, and time elapsed, an accurate nocturnal clock was as vital as a steady wind. Without it, a captain could not know how far he had sailed since sunset, leading to disastrous miscalculations. Their solution may have been elegantly simple, a device we could call the Phoenician star clock. This was not a complex mechanism, but a brilliant application of observable astronomy. The key was the unmoving North Star, Polaris, around which the entire northern sky appears to slowly rotate throughout the night. Specific constellations like the Big Dipper or Cassiopeia act like the hands of a giant clock face centered on this celestial pole. A Phoenician navigator could have used a simple tool, perhaps a length of cord with evenly spaced knots or a set of marked stones to track this rotation. Here is how it might have worked. At the start of his night watch, he would select a bright star in a familiar constellation as his marker. He would then align a fixed reference point on the ship, like a specific spot on the masthead, with that star and the North Star. He would then move a bead along his cord or select a marked stone for that hour. As the night progressed and the Earth turned, that marker star would appear to drift away from his masthead reference. By observing how far it had moved along its circular path around Polaris and comparing it to his cord or stones, he could estimate how many hours had passed. He would have memorized the nightly dance of the stars for different seasons, knowing that in spring, the Big Dipper's handle pointed one way at dusk and another by dawn. This star clock transformed the vault of heaven into a reliable timepiece. It allowed the captain to log his night's run with remarkable accuracy. If he knew his ship made roughly 5 miles in an hour sailing before a steady wind, and his star clock told him 6 hours had passed. He could confidently mark 30 miles of progress on his mental chart. This constant, silent tracking of celestial motion was the heartbeat of their dead reckoning. It required no fragile technology, only keen observation and transmitted knowledge. A father would teach his son the star paths for each month, the way we might teach a child to read a watch. This lost instrument of knotted string and memory turned the predictable wheel of the cosmos into the most durable clock imaginable, a timeless guide for history's first great commercial explorers. The Phoenician star clock tracked time by the wheel of the heavens, but on the banks of the Nile, another civilization sought to impose perfect order on the cosmos itself. Their tools were the Merkit and the Bay, instruments of sacred architecture that may have found a second life guiding ships along the river of life. The Merkit was a master of precision, a simple sighting tool consisting of a horizontal bar with a central notch and a weighted plumb line hanging from it. A priest, known as a horologer, would use it at night to track the meridian transits of specific stars. He would set up 2 of these devices, aligning their notches with a north-south line. By watching a chosen star pass through both notches and noting the position of the plumb line against a marked scale, he could determine the exact hour of the night with incredible accuracy. This was how the Egyptians divided the darkness into 12 equal parts, regardless of the season, creating the world's first equal-hour timekeeping system. It was a ritual act ensuring temple ceremonies began at the perfect celestial moment and that the pharaoh's reign remained in harmony with the eternal cycles above. The Bay was its daytime partner, a humble V-shaped notch cut into the center of a palm leaf rib or a flat piece of wood. This acted as a rudimentary alidade, a sighting device. A priest would hold it up to his eye, peering through the slit to precisely align the foundations of a pyramid or the axis of a temple with a distant marker or the rising sun on a solstice. Together, these tools built a landscape of stone that mirrored the heavens, but the Nile was Egypt's true highway, a winding, life-giving ribbon through the desert. It takes little imagination to see how a practical river captain, perhaps one who had served on royal barges transporting stone for those very temples, might have borrowed this sacred technology. On a moonless night, a navigator could use a Merkit not to time a ceremony but to hold a steady course. By sighting on a bright star through the notch and keeping the plumb line steady, he could ensure his vessel did not drift from a true north-south bearing as he sailed a long, straight section of the river. The humble bay could be repurposed during the day to take bearings on landmarks. Holding the palm rib to his eye, he could sight through the slit at a distinctive palm grove on the east bank, then turn and sight a distant hill on the west, triangulating his position in the river's channel to avoid sandbars. For longer, more daring voyages down the Red Sea toward the fabled land of Punt, these tools would have been even more vital. Out on the open water, with featureless desert shores on either side, the Merkit could become a marine sextant. By measuring the altitude of the North Star above the horizon using the plumb line and scale, a navigator could estimate his latitude, knowing how far south he had traveled. The bay could be used to measure the angular distance between stars, helping to maintain an eastward course across the sea. This was the genius of pragmatic adaptation, taking instruments designed to anchor temples to the cosmos and turning them into tools to anchor ships to a safe passage. The Merkit and Bay whisper of a world where sacred knowledge and daily survival were not separate realms, but flowed together like the timeless waters of the Nile itself. Egyptian priests turned sacred instruments to practical use, but in one legendary institution, all the world's practical knowledge was gathered under a single roof. The Great Library of Alexandria was not merely a building, it was the brain of the ancient world. Within its vast halls and storerooms, scholars collected every scroll and book they could find, from the markets of Athens to the caravans from India. While we mourn its loss for philosophy and poetry, we rarely consider the specific, devastating blow it dealt to the art of navigation. imagine entire codices, not just single scrolls, dedicated solely to the science of the sea. There would have been treatises written by Phoenician captains detailing their secret routes to the Tin Islands of Britain, with notes on currents and landmarks. There could have been accounts from Carthaginian explorers like Hanno, who sailed down the West African coast, describing the coastlines, rivers, and peoples he encountered, information that would not be rediscovered for over 1,000 years. Perhaps there were scrolls from Arab traders explaining the precise timing of the Indian Ocean monsoons, or from Malay sailors describing the star paths to distant Spice Islands. Most tragically, there might have been technical manuals, the ancient equivalent of engineering schematics, for devices like the Yantra Roger or advanced versions of the Antikythera mechanism. These would not have been simple descriptions, but precise instructions for their construction and use. The library was a hub of reverse engineering and synthesis. A Greek scholar in Alexandria could have compared a Babylonian celestial diary with an Egyptian star chart and a Persian tide table, synthesizing a new universal system of navigation. The loss was not a single event, but a slow, agonizing series of fires and conflicts over centuries. Each time a wing of the library burned, it wasn't just parchment that turned to ash. It was entire schools of thought, whole lineages of technical knowledge that vanished forever. The burning of the library erased the blueprints for humanity's understanding of the planet. It set exploration back by generations, forcing medieval navigators to painfully relearn what ancient sailors had already mapped and mastered. The true instrument lost here was the collective memory of our species, a global network of wayfinding wisdom that shrank into fragments and folklore. We are left to wonder what single scroll from that library would have changed history. A map showing a clear passage to the Americas, a working design for a mechanical chronometer. That silence is the echo of the greatest navigation tool we ever had, and then foolishly destroyed. The silent loss of Alexandria's knowledge forced navigators to rebuild from fragments, but one empire held onto the practical genius of its Roman predecessor. The Byzantine Empire, spanning the eastern Mediterranean for 1,000 years, was a civilization of bureaucrats and merchants who needed precise logistics. To manage their vast trade networks and naval patrols, they may have perfected a simple yet transformative device, the stadiasmos, a shipboard odometer. We know the Romans used mechanical odometers on land, brilliant gearboxes attached to chariot wheels that dropped a pebble into a bin every Roman mile. The concept was straightforward. A wheel's rotations were counted, and after a specific number, a mechanism triggered a marker. Translating this to the sea seems a logical leap for an empire that lived by maritime trade. Imagine a Byzantine dromon, a swift warship on patrol. Mounted on its hull, a small, specially designed paddle wheel trails in the water. As the ship moves forward, the current turns this wheel. Inside the ship, connected by a simple axle, is a compact gear train, a direct descendant of the Roman land odometer. For every certain number of paddle wheel rotations, calculated to represent a specific distance like a nautical mile, the gears complete a cycle and release a small stone or lead ball into a waiting copper basin. Clunk, the ship's officer, perhaps the Kentachos or captain, hears the sound and makes a notch on his wax tablet. Clunk, another mile. This steady, mechanical click provided a continuous, approximate measure of distance traveled through the water, the single most vital piece of data for dead reckoning in the relatively predictable currents of the Mediterranean. It removed pure guesswork from the equation. A captain sailing from Constantinople to Crete could consult his periplus and know the total distance was, say, 500 miles. If his stadiasmos clicked 500 times, he knew he needed to start looking for land, regardless of how many days the voyage had taken or how variable the winds had been. It was a primitive speed log, transforming time and intuition into a tangible, countable measure. The profound utility of such a device is undeniable, yet not a single maritime odometer has ever been found on a shipwreck or depicted in Byzantine art. Its existence remains a compelling theory, a ghost in the machinery of history. Was it a state secret, its design guarded by the Imperial Navy, or were the devices so valuable they were salvaged from every sinking vessel? Perhaps they were simply made of common materials, wood and cheap metal, that corroded into nothingness on the seafloor. The Stadiasmos represents a tantalizing might-have-been, a mechanical heartbeat for the Empire's ships, counting out the miles that held an ancient world together. The Byzantine odometer counted miles on predictable seas, but far to the north, another culture faced a wilder, cloud-shrouded ocean. The ancient Celts are rarely remembered as master mariners, their legacy tied more to hill forts and intricate metalwork than to the open sea. Yet archaeological finds of Celtic artifacts on distant shores and the accounts of Roman historians hint at a people with surprising nautical reach. They traded across the stormy Bay of Biscay and likely reached the shores of Britain and Ireland long before the Romans. To navigate these treacherous, often overcast waters, they may have relied on a tool as elegant as their knotwork, a device we could call the Celtic lunette. This was not a complex geared mechanism, but a crescent-shaped piece of carved wood or beaten bronze, its curved edge mirroring the phases of the moon itself. The Celtic world was deeply attuned to lunar cycles, their calendars and festivals meticulously aligned with the moon's journey. It is a short, logical step to believe this celestial reverence had a practical application. On a night when scudding clouds blotted out the familiar stars, the moon could still cast a diffused glow. A navigator could hold the lunette aloft, aligning its horns with the visible crescent of the moon. By noting how the moon's curve fit within the tool's predefined arc, he could estimate its phase with greater precision than the naked eye allowed. This was crucial because the moon's phase dictates the tide, the most powerful and dangerous force on any coastal voyage. Knowing whether a full moon spring tide or a neap tide was due could mean the difference between safely beaching a coracle on a sandy shore or being dashed against rocks. Beyond tides, the lunette could have served as a simple sextant. By holding it vertically and sighting along its edge to the moon's highest point in the sky, then reading markings along the curve, a sailor could measure the moon's altitude. This measurement, compared to remembered values for certain times of year, could provide a rough estimate of latitude, a north-south position. The moon moves more quickly and complexly than the stars, making it a trickier guide, but for a culture that tracked its cycles with religious devotion, its path would have been intimate knowledge. Imagine a Celtic boatman guiding a hide-covered currach along a foggy coastline, the land a mere shadow. He pulls a smooth, dark piece of yew wood from his tunic, its crescent shape worn smooth by generations of hands. He holds it up to the silver sliver in the sky, nods once, and turns his vessel confidently toward a hidden estuary he knows will be safely flooded. The lunette transforms from a speculative tool into a symbol of a different kind of wisdom, one that wove practical survival into the very fabric of cosmic belief. A Celtic navigator's lunette connected him to the rhythms of the moon, but what if an entire trade route could be learned without ever leaving dry land? This brings us to a truly speculative yet captivating idea, the possibility that ancient board games were not just pastimes but sophisticated navigation trainers. Across the Arabian Sea region, from the ruins of the Indus Valley civilization to later Arabian settlements, archaeologists have unearthed intricate game boards carved into stone or etched onto clay tablets. These are not simple race games, but complex grids of squares and symbols, often accompanied by collections of distinctive playing pieces. For a long time, they were catalogued merely as entertainment, the ancient equivalent of chess or backgammon. But a compelling theory suggests they might have been something far more vital, a classroom in a box for aspiring merchant captains. Think of the board as a symbolic map of the Arabian Sea. The grid could represent the predictable wind matrix of the monsoon system, those powerful seasonal winds that dictated all travel across the Indian Ocean. Different colored squares might indicate favorable winds, doldrums, or dangerous seasonal storms. The playing pieces, perhaps carved into shapes of ships or animals, could represent different types of vessels, a sturdy dhow versus a swift canoe, each with its own capabilities. The goal of the game would not be simply to reach the opposite side, but to navigate a course from one specific port, say Lothal in the Indus Valley, to another like Oman or Mesopotamia. Players would draw cards or cast lots representing real-world variables, a sudden shift in the wind, a pirate sighting, a leaking hull. They would then have to use their pieces to navigate this hazard on the symbolic sea, learning through play which routes were safest at which time of year, where to find freshwater stops along the barren coast, and how to conserve cargo space for the journey home. A master trader would teach his apprentices not with a dangerous voyage, but over a game board in the cool of the evening, drilling the patterns of the ocean into their minds until they became instinct. The tragic loss, then, is not of the physical boards but of the rules. Without the scroll or the oral instructions that explained what each symbol meant and how the hazards interacted, these beautiful artifacts are silent. We see the game board, but we cannot play the game. The intricate knowledge of monsoons, currents, and ports that was once encoded in this playful system has evaporated, leaving behind a beautiful but baffling curiosity. What was once a dynamic simulator for wealth and survival is now a static puzzle in a museum case, a locked door to a lost school of the sea. The silent game boards of the Arabian Sea held routes in their grids, but in ancient China, navigational secrets were etched onto a far more permanent and mystical medium. Deep in the royal archives of the Shang dynasty, over 3,000 years ago, scribes carved questions for the gods onto the shoulder bones of oxen and the plastrons of turtles. These oracle bones are famous for revealing the dawn of Chinese writing, but among the prayers for rain and predictions of harvest, some inscriptions hold a more earthly mystery. They speak of journeys. Specific characters denote directions like east, west, or going downstream. Others record distances measured in days of travel or mention places beyond the Shang capital. A bone might ask, if we send a party to the river mouth, will we receive safe passage? Or is the 10th day auspicious for traveling to the lands of the Qiang? For decades, these were studied purely as records of divination. Yet a compelling theory suggests they are something more: the cryptic logbooks of China's earliest state-sponsored navigation. The Shang heartland was the Yellow River Valley, a volatile, shifting waterway that was both a life source and a formidable challenge. Controlling trade and communication along its length was essential for power. The Oracle Bone inquiries about downstream travel likely refer to expeditions to collect precious resources, seashells from the coast for currency, or salt from specific marshes. The responses from the gods, interpreted by priests from the cracks made by hot bronze rods, would have granted divine sanction for these risky ventures. But the practical information, the actual routes, distances, and landmarks must have been known to the expedition leaders. That knowledge may have been encoded right there in the ritual. The mention of a 10-day journey to a specific tribe could simultaneously be a spiritual query and a record of a known travel time. A request for auspicious winds might correlate with the seasonal patterns on the Yellow River. These bones then become a dual record, a spiritual insurance policy layered over hard-won geographical intelligence. The loss is profound. While we can decipher many of the characters, the full context is gone. We do not know the exact location of most places named. We cannot reconstruct the maps that must have existed in the minds of those Shang boatmasters. The Oracle Bones are a locked archive of Bronze Age wayfinding, their practical meaning burned away by time, leaving only the ghostly outline of journeys taken under the watchful eyes of ancestors and gods. They remind us that the first maps were not drawn on parchment but inscribed on bone, written in a language of destiny and direction we can only partially understand. Oracle bones recorded journeys for kings, but in the vast Pacific, navigators created charts you could feel with your hands. The Micronesian stick chart is a rare survivor, a physical artifact that proves ancient sailors thought in 3 dimensions. Yet the very existence of these beautiful, web-like frames of palm ribs and shells poses a deeper mystery. The stick charts we have in museums are not maps of land, but models of the sea itself. They are teaching tools crafted from durable materials to last. They represent the patterns of ocean swells, the refracted waves bouncing off distant islands, and the intersection points of currents. A shell tied at a crossing of sticks might not mark an island's location, but the specific felt sensation of the waves in that region. A novice navigator would learn by running his fingers over this skeletal chart, memorizing the rhythm of the ocean it encoded. But what about the original charts, the master references from which these teaching models were derived? These are the truly lost instruments. We can theorize they were far more comprehensive, perhaps drawn in the sand with a finger, or woven from fragile pandanus leaves and fibers that disintegrated after a single voyage. These ephemeral master charts could have encoded not just local wave patterns, but the entire symphony of swells across an ocean basin. A master navigator, before setting out from his home atoll, might sit with his students and weave a new chart for a specific journey. As he spoke, he would lay down fibers to represent the dominant swell from the east, then cross it with others showing how that swell bent around the target island 500 miles away. He might tie a special knot where a secondary current from the north created a telltale choppy confusion. This living chart was a one-time diagram of energy, a dynamic forecast for that particular trip under those seasonal conditions. Once the voyage was over, the chart, having served its purpose, might be discarded, its knowledge now residing solely in the navigator's mind and in the simplified, durable stick model left behind for teaching. The loss, then, is not of the concept but of the full, rich data set. We have the simplified textbook diagram, but the original, complex scientific paper written in palm fronds is gone. It means we see the shadow of Micronesian genius, but not its full, brilliant light. These master charts represented a fluid, living cartography that viewed the ocean not as empty space to be crossed, but as a vibrating network of force and rhythm, a language of water that only the most educated could read. The Micronesian charts were woven from ocean swells, but one of history's most daring voyages left behind only a cryptic text. The Periplus of Hanno is a tantalizing fragment, a Greek translation of a report from a Carthaginian admiral who sailed beyond the Pillars of Hercules around 500 BC. His mission was to found colonies and explore the terrifying west coast of Africa. The text describes a journey past rivers of fire, mountains that touched the sky, and encounters with what he called gorillas, likely a tribe of great apes. It reads like a fantastical adventure, but modern scholars believe it contains real geographical observations of volcanoes, jungle-covered peaks, and even the mangrove swamps of the Gulf of Guinea. This raises a crucial question: how did Hanno and his fleet of 60 ships navigate such an unknown and hostile coastline for months, even years? The text we have is a summary, a digest meant for public consumption. The real navigation tool, the one lost to us, was almost certainly a physical companion to this log, carried on the flagship itself. This would have been the admiral's personal pinax, a wooden tablet coated in wax. Unlike a static map, this pinax would have been a dynamic instrument. As the fleet sailed, a scribe or the navigator himself would have used a stylus to etch the day's progress directly onto the wax. The tablet might have shown a rough, evolving coastline, with notches marking each new river mouth or distinctive headland described in the text. More cleverly, it could have employed a simple moving part, a small wooden peg or a piece of string that could be adjusted to represent the ship's estimated position relative to the last known landmark. This moving marker would have been the heart of their dead reckoning. Each day, based on the observed speed and the prevailing wind direction, the peg would be shifted southward along the etched coast. When they finally sighted the next major landmark, a towering volcano perhaps, they could correct the peg's position, reconciling their estimate with reality. This pinax was more than a map, it was a continuous calculation, a thinking tool. The textual periplus gave the narrative, but the wax tablet held the geometry. It translated the epic descriptions of roaring fires at night, which were likely grass fires set by tribes or volcanic activity, into practical bearings, a warning that such a sight meant you were approaching a specific bay. The loss of this physical companion is profound. We have the story, but we lack the interactive worksheet that made the story possible. It represents the messy, hands-on reality of ancient exploration, where grand ambition met the daily grind of marking a wax slate, of trying to fit the terrifying unknown into a manageable, movable diagram. That worn tablet, its wax scarred with corrections and guesses, was the true instrument that guided men beyond the edge of the known world. Hanno's wax tablet plotted a course along an unknown coast, but on the opposite side of the world, another coastal people perfected a tool for the daily journey home. The Moche civilization of ancient Peru, famed for their intricate goldwork and vivid pottery, thrived along a narrow strip of desert between the Andes Mountains and the Pacific Ocean. Their lifeblood was the Humboldt Current, a cold, nutrient-rich stream that created one of the world's richest fisheries. Moche fishermen ventured far out onto the open ocean in their reed boats, chasing schools of anchovy and larger prey. From their perspective, the coastline was a nearly unbroken line of desert cliffs, with only the mouths of seasonal rivers breaking the monotony. How, after a day of drifting with the currents, did a fisherman know he was sailing back toward his own river valley and not the next one 20 miles north? The answer may have been a brilliant, organic device we could call the Moche fisherman's sextant. This was not a brass instrument of astronomers, but a practical tool carved from a dried gourd or a flat piece of driftwood. Its design was likely elegantly simple, a flat plane with a small vertical sighting pin at one end and a series of carefully marked notches or holes along a curved edge. At local noon, when the sun reached its highest point in the sky, the fisherman would hold the base level and look along the sighting pin toward the sun. He would then slide a movable bead or a piece of cord along the curved track until its shadow aligned with a specific mark. The position of that bead against the pre-marked notches would tell him the sun's exact altitude. This number was his latitude in the sky, because each river valley sat at a slightly different latitude along the coast. Knowing this solar angle was like reading his home address in the heavens. If the sun's noon altitude was higher than when he left, he had sailed too far south and needed to head north. If it was lower, he had drifted north and must turn south. This constant daily check allowed him to sail a parallel course to the coast, staying directly offshore from his home port even when it was invisible beyond the horizon. The tragedy of this ingenious tool is its perfection for its environment. Made entirely of biodegradable materials, gourds and wood and cord, not a single example has survived in the archaeological record. The acidic soils and humid microclimates of the coast would have consumed them completely within a few generations. We infer its existence from the Moche's undeniable mastery of their maritime world and from the later, similar tools used by their descendants. It was a democratized piece of celestial technology, not locked in a temple but held in the calloused hands of every working fisherman. This simple sextant turned the terrifying expanse of the Pacific into a measured grid, where the sun at its peak became a fixed point of return, guiding each boat home to its own specific strip of desert shore. The Moche fisherman's sextant was a personal key to the coastline, but it represented a single note in a vast symphony of unwritten knowledge. This brings us to the final, and perhaps most profound, instrument on our list, one that was never carved from wood or forged from bronze. The ultimate lost navigation tool was the global thread of oral tradition itself. For thousands of years across every ocean and continent, the true guidance system was not a physical object but a living database held in human memory. This was a knowledge so deep and nuanced that it took a lifetime to master. An apprentice navigator, whether in Polynesia, Scandinavia, or the Arabian Sea, did not simply learn to use a tool. He spent years, often decades, committing an entire world to memory. He learned not just the rising points of stars, but the subtle shifts in their paths with the seasons. He memorized the specific flight patterns of seabirds, knowing which species flew out 50 miles from land and which stayed close to shore. He could read the shape and texture of clouds on the horizon, identifying the unique formations that gathered over unseen islands. He learned to taste the salinity of the water and to recognize the slight changes in its color, from deep indigo to shallow turquoise, that spoke of distant reefs or river plumes. He knew the smell of the wind, how it carried the scent of mangrove swamps or desert dust from lands still beyond sight. This was a holistic science of observation, where every sense was calibrated as an instrument. A master navigator was a library of the natural world. He held star paths, wave patterns, animal behaviors, and atmospheric clues in a complex, interconnected mental map. This knowledge was transmitted through chants, stories, and songs, rhythmic devices that made vast amounts of data easier to remember and pass on. The loss of this oral tradition is the greatest silence in the history of exploration. It did not vanish in a single fire or shipwreck. It faded slowly over generations as new technologies arrived. The magnetic compass gave a simple, constant direction. The written chart fixed a coastline permanently on parchment. The marine chronometer finally solved the longitude problem. Each was a magnificent breakthrough, but each also made a piece of the old, all-encompassing knowledge seem less essential. Why spend 20 years learning to read the waves when a compass points north? Why memorize the stars for every night of the year when a printed almanac can tell you? The exquisite, nuanced language of the sea, spoken fluently by ancient mariners, gradually fell out of use. The last masters of these traditions took their comprehensive understanding with them, and the living instrument that once guided humanity across the planet became a whisper, then a rumor, and then silence. We are left with the tools we can hold in our hands, the fragments of wood and metal, wondering at the greater wisdom that once animated them. The true map was never on a tablet. It was written in the minds of those who listened to the world and remembered. The silence of those lost navigators leads us to a darker question. Why did so many of these brilliant instruments vanish in the first place? The answer is not a single event, but a slow, relentless process we might call the Great Forgetting. These tools disappeared for reasons as varied as the cultures that created them, and their loss was rarely a simple accident. First, consider the sheer fragility of the materials themselves. The most elegant wave chart woven from palm leaves, the polished gourd sextant of a Mach fisherman, the wax tablet of a Carthaginian admiral, these were organic, ephemeral objects. They were designed for use, not for eternity. A single monsoon season, a shipwreck, or the simple passage of a few decades could erase them completely, leaving no physical trace for archaeologists to find. Their knowledge lived only as long as the people who remembered how to weave them or read them. Then there was the deliberate veil of secrecy. For many ancient mariners, navigation was not a public science but a source of power and wealth. The intricate knot on a camel's string was a trade secret as valuable as a map to a gold mine. A Phoenician captain's star clock knowledge was a family inheritance passed only to a chosen son. Guilds and master navigators guarded their methods fiercely, understanding that their unique skill guaranteed their employment, their status, and their community's survival. This secrecy was a double-edged sword. It protected valuable knowledge in the short term, but it also made that knowledge incredibly vulnerable. If a master died without a fully trained apprentice, if a guild was wiped out by plague or war, their entire system of wayfinding could vanish overnight. The knowledge wasn't stored in a library, it was stored in a few human minds, and when those minds were gone, the instrument, whether physical or mental, was lost forever. Sometimes the scale of loss was catastrophic, an entire civilization collapsing and taking its tools with it. The Late Bronze Age collapse around 1200 BC is a prime example. In a relatively short period, the interconnected empires of the Eastern Mediterranean, from the Mycenaean Greeks to the Hittites to the coastal Canaanite cities, fell into ruin. Palaces burned, trade routes disintegrated, and literacy itself nearly disappeared. In that chaos, what happened to the sophisticated paraploy of those sailors? What happened to the celestial almanacs used by merchants sailing between Cyprus and Egypt? They were almost certainly consumed in the fires that destroyed the port cities and administrative centers that held them. A societal collapse doesn't just topple buildings, it shatters the complex networks of specialized knowledge, scattering the fragments until they are unrecognizable. The Minoan wave readers and any instruments they used were likely victims of a similar earlier disaster. Perhaps the most ironic cause of loss, however, was not disaster but progress itself. The invention of new, simpler technologies often rendered the old, complex ones obsolete. The widespread adoption of the magnetic compass, for instance, was a revolution. Here was a tool that pointed north reliably, day or night, in clear weather or fog. Why spend years learning to calibrate a Viking bearing dial with a sunstone when a sliver of magnetized iron floating in a bowl of water could tell you your direction instantly? Why maintain the vast oral tradition of reading subtle swell patterns when a compass gave you a constant, unwavering reference? The new tool was a democratizing force, making navigation accessible to more people, but it also made the deep, environmental wisdom of the past seem unnecessarily difficult. The old masters and their intricate methods were no longer in demand. The instruments were not destroyed, they were simply put aside, forgotten in a chest, and eventually discarded when their purpose was no longer understood. This technological displacement was a quiet, efficient form of forgetting, where the brilliance of the past was erased not by fire but by convenience. The Great Forgetting teaches us that loss is woven into the fabric of history, a shadow that follows every leap forward, leaving us to wonder what essential wisdom we, in our own age of digital certainty, might be allowing to silently slip away. These ancient instruments are not simply relics of a forgotten past. Their ghosts are embedded in the technology we use today, a direct lineage of human ingenuity stretching across millennia. Consider the Polynesian star compass, that mental map of the heavens. Its core principle, using the predictable positions of celestial bodies to determine location, is the very foundation of modern celestial navigation. The star compass has been digitized and amplified. Today, sailors and even some military units use software that can instantly calculate a position from a star sighting, performing in seconds the complex spherical trigonometry that a master navigator once held in his mind. It is the same conversation with the cosmos, now conducted through silicon and code. Similarly, the humble camel, with its knot marking a specific latitude, is the direct ancestor of the marine sextant. Both tools measure the angular height of a celestial body above the horizon. The camel's wooden card and string were a fixed physical memory, while the sextant's precise arc and vernier scale allow for dynamic, adjustable measurement. The goal, however, is identical: to find your north-south line on the globe by locking onto the sky. The most profound echo, however, comes from the Antikythera mechanism. This intricate Greek clockwork, with its interlocking gears modeling planetary motions, is now recognized as a direct conceptual forerunner to the analog computer. Its purpose, to process inputs, crank a handle, and produce a predicted output based on a mechanical program, is the fundamental logic of computation. We have replaced bronze gears with transistors and its hand crank with electricity. But the ambition to build a machine that can model complex systems began on that Mediterranean shipwreck over 2,000 years ago. This historical loop is now being closed in the most fascinating way. Modern engineers and historians are using the very technology these ancient tools foreshadowed to bring them back to life. Through high-resolution, three-dimensional scanning, they can peer inside corroded lumps like the Antikythera fragments without ever touching them, revealing hidden inscriptions and gear teeth invisible to the naked eye. Advanced material science allows them to analyze microscopic wear patterns on artifacts, determining how a Viking sunstone was held or how a bearing dial's gnomon was polished by use. They use computer modeling to simulate how these devices would have functioned, testing theories of operation in a digital space before attempting physical reconstructions. In a beautiful symmetry, we are now using computers to understand the world's first computer, employing laser scanners to decipher the secrets of starstones and applying astrophysics software to validate the accuracy of ancient star charts. Each discovery validates the sophistication of our ancestors, proving that their lost instruments were not crude guesses, but refined technologies born from deep observation and brilliant problem-solving. The quest to find them has become a conversation across time, where our most advanced tools are finally allowing us to hear the whispers of the first navigators and to understand the full scope of the maps they carried, not in their hands but in their minds. From the frozen north to the tropical Pacific, we have traveled across a hidden atlas of forgotten genius. 25 lost instruments, each a unique key to unlocking the ancient world. They were crafted from every material imaginable, from Viking sunstones that captured hidden sunlight to Polynesian mental maps that charted the stars, from the intricate brass gears of the Antikythera mechanism to the simple knotted string of an Arab camel. This was not a single story, but a global symphony of innovation, where every culture, facing its own unique sea or river or desert, engineered its own brilliant solution. The diversity is staggering, proof that the drive to explore and the ingenuity to navigate are fundamental threads in the human story. The true weight of these discoveries lies not just in their cleverness, but in their silence. Their loss carves deep gaps into our understanding of history, reminding us that the past we know is only a fragment of what once was. For every parchment that survived, 100 wax tablets melted. For every bronze instrument preserved, 1,000 wooden tools returned to the earth. These silent gaps are humbling. They force us to reconsider the ancient world not as a primitive prelude to our own, but as a landscape populated by sophisticated thinkers, engineers of their environment, who solved monumental problems with the materials and knowledge they had. They observed the natural world with a depth we can scarcely comprehend, turning waves into maps and star paths into highways. Their tools were extensions of a profound, attentive wisdom. So we are left with a question, one that echoes across all those silent oceans. Which of these lost instruments captures your imagination the most? Is it the mysterious sunstone, a crystal that seems to bend the rules of perception? Or the living, breathing knowledge of the Micronesian master navigator, holding an entire ocean in his mind? Perhaps it is the haunting ghost of the Library of Alexandria, the collective brain of the ancient world lost to fire. Share your choice in the comments below and let us know which historical mystery you would want to explore next. If you enjoyed this journey into the lost tools of exploration, be sure to subscribe. Our next adventure into the shadows of history is already on the horizon.